is my great pleasure to welcome you to the second of Lenny Suskind's 3 messenger lectures. Based on the number of people who stepped up to us and introduced themselves to Lenny and tell him how thrilled they are to meet him in person, ignoring me, I think I need an introduction more than he does. So, I'm Paul Ginsberg. I'm a professor of physics and information science here at Cornell. And I'll say a few words about this particular lecture series and then give a short introduction to Lenny. So Cornell's messenger lectures were established in 1924.
Oh, can I ask you to call me by my actual given name, Leonardo?
Leonardo de Susskind. By a gift from Dr. Hiram de Messenger, Dr. Hiram Messenger, a Cornell graduate of 1880 and a longtime teacher of mathematics. The terms of the original gift established, pay attention, a fund to provide a course of lectures on the evolution of civilization for the special purpose of raising the moral standard of our political, business, and social life. There was a period when anyone who was anyone in the pantheon of physics was a messenger lecturer here, going back to R.A. Millikan, 1925, remember the oil drop. Sir Arthur Eddington, 1933, remember the solar eclipse in 1919. J. Robert Oppenheimer in 1945, well, Fred Hoyle in 1960. Richard Feynman, 50 years ago, 1964, up to including recent messenger lectures in the past decade. Sir Martin Rees, Stephen Weinberg, Nimar Khani Hamed. I was told to ask, out of curiosity, how many of you were here for Feynman's lectures 50 years ago? So I count about 10 or 15 people. After the lecture on Monday, I was thrilled to, somebody who was an undergraduate visiting his children here told me the same thing. Now, tonight's speaker, Lenny Suskind, was born in the South Bronx of New York City in 1940, went to City College of New York, came to Cornell in 1962, both to escape taking over his father's plumbing business in the South Bronx and also to receive a PhD in theoretical physics in 1965. He went to Berkeley, was on the faculty of Yeshiva University until 1979. Since then, has been a professor at Stanford, including most recently since 2009, the director of the Stanford Institute for Theoretical Physics. He's one of the founders of string theory, actually the one who introduced the notion that particles could be described by excitation states of a relativistic string. Has 4 decades of over 200 cutting-edge research articles, still growing rapidly. He's one of the, he has various awards, National Academy of Sciences, American Academy of Arts and Sciences. I'll read only his J.J. Saccharai's prize citation for pioneering contributions to hadronic string models, lattice gauge theories, quantum chromodynamics, and dynamical symmetry breaking. His expository gifts have carried over to the popular realm. He's authored a number of popular books on subjects from cosmology to black holes to quantum mechanics. He's been on Nova shows discussing various aspects of physics. On this, I have to move this over. For this poster, I took a screen grab in the upper left from his popular book on black holes and information theory, because he told me at lunch today the audience would be very disappointed not to see at least one picture of an actual black hole at this time. There's also, I think that might be a galaxy. You also could listen to this. And he has a large number of online lectures. This was absolutely extraordinary to me. This is what people know. I searched for Leonard Susskind in Google videos. I don't know if you can see it. This is not a hoax. 281,000 results for videos of Leonard Susskind, Leonardo Susskind, on everything, popular lectures, the theoretical minimum, and all of the rest. So everything from my friend, Richard Feynman, to my battle with Stephen Hawking. So what I'm going to do now, and it's with great trepidation as to whether or not this is going to work, I'm going to set it up. In honor of this being the second lecture in the 50th anniversary, I'm going to show a 2-minute clip, which you'll see is entirely appropriate, but also great fun, from Feynman's second messenger lecture. I'm going to stop it at one point for an essential observation. Let's see if this works. Identical black used by Feynman. Now, when he comes on, he's going to say something about how he had been blinded by the lights in the first lecture, and he's happy to be able to see the audience. But I want it on record that in none of his lectures did he ever complain about the black people. Now, the words he uses will also be an incredibly prescient 50 years earlier second lecture, an introduction to tonight's lecture.
Hi. I can see the audience tonight, so I can see also from the size of it, which last time was a black spot in front of my eyes, that there must be many of you here who are not thoroughly familiar with physics. And also a number that are not too versed in mathematics, and I don't doubt that there are some who know neither physics nor mathematics very well. That puts a considerable challenge on a speaker who is going to speak on the relation of physics and mathematics, a challenge which I, however, will not accept.
Let us welcome Lenny Susskind.
All right, I have a couple of things to say before I start. The first thing I want you to know is that I actually did bring a jacket and tie to Ithaca with me. I'm not wearing it, but I did bring it. You know what? I'll prove it next time. Dick was better dressed than I am. The second thing I wanted to talk about was the way I begin lectures. I often write out a couple of paragraphs, and then I actually read them Sometimes I don't. And somebody asked me, why do you sometimes do this and why do you sometimes not do it? And the answer is it really does depend on what I had to drink before I lecture. Tonight I had a couple of beers, so I have this terrible fear of completely forgetting what I'm supposed to talk about, and so I write a few paragraphs to get me started. So if you don't mind, I will begin by reading my paragraphs. But even before that, I want to second the thing that Dick said. I actually don't know how to aim a lecture like this. I really don't. I have the feeling that, that my problem is similar to our President Obama's. Anything I say will leave almost everybody dissatisfied. But here goes. Quantum mechanics is confusing. I think we will all agree. Oh, actually, I'm not sure. David Merman probably doesn't agree. He understands it better than we do, but apart from David, yes. One of its peculiar features is there are often different descriptions of the same thing that sometimes seem incompatible to our classical minds. A couple of examples that come to mind are the fact that the electromagnetic radiation is sometimes described as waves and sometimes described as particles, but not both at the same time. Another one is that particles have positions, particles have velocities, but not both at the same time. This is confusing. If an electron can have a position and that same electron can have a velocity, how can it not have a position and a velocity? All of this has a name. At least I think it's the right name. It's called complementarity. Now, the reason I'm not sure is I don't think anybody ever had the vaguest idea of what Bohr was talking about when he talked about complementarity, but that's the way I'll use it. That there are complementary descriptions of things that at first sight look truly incompatible. Now, how does nature avoid contradictions? The answer is that she never allows us to measure incompatible properties at the same time. We cannot measure both the number of photons and the phase of an electromagnetic wave. We can at most measure one or the other. The same is true for position and velocity of a particle. We might say that an electron does not have a position and a velocity. It has a position or a velocity. Black holes are very strange objects, to be sure, but black holes in a quantum mechanical world are worse than strange. They appear to contradict deeply held principles. However, a strange kind of large-scale complementarity is at work, which again allows us to avoid contradictions, but just by the skin of our teeth. I will do my best to explain. I hope nobody has a gun. The last time I explained something a little bit called information conservation. Before I actually start to talk on the blackboard, I just want to remind you about what information conservation means. The equations of physics never allow information to disappear. Let me give you an example of something that looks like information is disappearing. Here's a box of some sort. I'm going to slide it across the table. No matter how I start it, no matter how fast I start it, no matter which way I give it a push, it comes to rest. It comes to rest someplace on the table. There are many different starting points that might lead it to come to rest at the same place. It seems like it's lost information. Now, of course, we all know what happened. What happened is it heated the table underneath. It excited the molecules. Heat was formed by friction, and the object slowed down. Why? Because energy got transferred to the table. Not just energy that got transferred to the table, the information of the starting point also got transferred to the table. If I could reconstruct every single molecule, every single degree of freedom in the table, I could, in principle, not in fact, but in principle, recover exactly what had happened to the box. I would, of course, have to include all the air in the room and everything else. There's hidden information in the world, hidden often because it's hidden in degrees of freedom which are too small and too numerous to keep track of. This hidden information has a name. It's called entropy. All right, that was by way of reminding you of what I said last time. That's really all we'll need from what I said last time. Now I want to start by discussing the equivalence principle. I told you last time that my interest in these lectures was going to be conflicts of principle, and it will be true. We will be talking about the conflict of the principle of information conservation and the equivalence principle. So let me remind you what the equivalence principle is. The equivalence principle is, of course, about an equivalence. It's the equivalence between acceleration and gravity. If I was standing here, not in a room with a gravitational field, but I was standing in an elevator that was accelerating upward, Einstein's elevator, I would feel exactly the same thing as I feel sitting here in this room. Instead of gravity, we would have the acceleration. If I took this, I better not throw this. Here's something I can throw. If I did this, or I was juggling or something, I would have exactly the same experience if I were in the upward accelerated elevator or if I were in the gravitational field. So a uniform gravitational field, keep in mind for the moment uniform, a uniform gravitational field is exactly the same as a field of acceleration, let's call it. Let's pursue that a minute. Let's think of an observer, a person who is in uniform acceleration along the x-axis. Normally I think of the vertical axis as the z-axis, I don't know why, but I'm going to use for the vertical axis the time axis. So for the moment, we'll just think of uniform acceleration along the x-axis, and the equation for uniform acceleration along the x-axis, I think probably most of you have seen it, is that the position of an object is the starting position, call it x naught, plus 1/2 g. G is the acceleration of gravity. In this case, we're talking about a gravitational acceleration times t squared. There's another term that I could put in to represent the initial velocity, but I'm going to leave it out. This is the formula for uniform acceleration. It would describe my trajectory if I were in an accelerated frame instead of standing still. All right, now one of the things about this formula, which tells you immediately that it can't really be the real truth, is that it also says that the velocity is equal to g times t. What does that mean? That means if you wait long enough, you'll achieve any velocity, and you know you can't achieve a velocity greater than the speed of light. So this has to break down. In fact, with the ordinary acceleration of gravity, it would take about a year, and after a year, this formula would say you're moving with the speed of light. A year and a half, and you'd be moving 1.5 times the speed of light. So this can't be right. This can't be the right formula. Not in special relativity in any case. So let me show you what a uniformly accelerated frame of reference looks like in special relativity. I'll draw it by beginning with a drawing of space-time. Here's space-time. The vertical axis now is time, but I won't draw it. Whenever a physicist starts drawing space-time, chances are he will draw two diagonal lines. The two diagonal lines represent the light cone. They represent the trajectory of light rays going to the right or light rays going to the left. There are two other directions of space, time, x, two other directions which I can't draw on the blackboard. The blackboard just doesn't have enough directions, and so I have to leave them to your imagination. Now, a uniformly accelerated trajectory is one which looks like a hyperbola. The formula that I wrote before would be a parabola. X equals 1/2 gt squared, or 1/2 plus an extra constant. The right formula for a uniformly accelerated observer would be a hyperbola. And that hyperbola would eventually become very, very close to the light rays. The meaning of that is a uniformly accelerated observer in special relativity asymptotically moves with the speed of light. Apparently stops accelerating, but of course in his own frame of reference he is accelerating. Now we can introduce a clock. Imagine that the observer has a clock, and let's tick off the observer's clock ticks. This is t equals 0. This is t equals 1. And up here somewhere is t equals 2. And if we keep going up and up and up, asymptotically we'll come to t equals infinity. We can draw this a little bit differently. we can imagine a family of observers. Imagine a family of observers, and we can draw a time axis here. Not a time axis, a surface that we'll call t equals 0. Everywhere along here is t equals 0. Everywhere along here is t equals 1 for the accelerated reference frame. Everywhere along here is t equals 2. As we keep letting time go forward, eventually t equals infinity becomes this light-like line there. That's what, for those who are not familiar with this is new. You won't recognize it immediately, but this is what it looks like to have a uniformly accelerated reference frame. Okay, now let's call this observer here, let's give her a name. This is Alice. Why Alice? Well, for those who aren't physicists all know that the two physicists in the world are Alice and Bob. Alice and Bob were two names that were, I don't know who first introduced them, but they represent two observers. I think people just got tired of saying observer A and observer B. They became Alice and Bob. When you need a third one, it becomes who? Charlie, of course. I don't know who the fourth one is. That's Eve, the eavesdropper, but who's the fourth? I don't know. David. Okay, so this is Alice. So far we haven't introduced Bob. Okay, and Alice is moving like that. What can Alice see? What's in Alice's experience? This is what I want to ask. What can Alice look out and see? So what she can see has to do with the light rays that she can eventually detect. For example, if a light ray from here, from this point over here, comes up and hits Alice, she can see that point. So this is a point that Alice can look back and see by virtue of a light ray hitting her over here. Here's another place that she can see. She can see this place. She can look back and see that point, this point of space and time over here. In fact, she can look back and see everything to the right, to the lower right of this 45-degree line here. But she cannot see anything up in here. Why? Because no light ray from here can reach Alice. So from Alice's perspective, Alice, who is eternally accelerated, forever and ever and ever keeps accelerating, this portion of space-time here is not part of her observable world. Well, let's not cross it out for the moment. Alice's observable world is to the right here, and Alice would call this line here a horizon. She can see nothing beyond it. Can that be read? Horizon. Yeah. She can see nothing beyond it. This is Alice's world. Okay. Now let's introduce Bob. Let's make another picture for Bob. This one is getting too cluttered. Here's another picture for Bob. Bob is a fellow who doesn't mind falling past this line. He's not uniformly accelerated. He's just in free fall. Free fall means he moves on a straight line, and so he's just perfectly free. He is not dragged along by the accelerated reference frame. He just falls through over here. So here's Bob. Here's Bob. Here's Alice. Alice looks back and sees Bob. Bob can also look back and see Alice. In fact, Bob can continuously look back and see Alice. He never loses track of her, but Alice loses track of Bob. Once Bob crosses here, she cannot see him anymore. In fact, the way Alice observes Bob is she keeps looking back from later and later time. She looks back from later and later times and gradually sees Bob approach this point. She can never see him cross that point because she can never get light from behind this point. And in fact, it appears to her to take Bob an infinite amount of time to cross that horizon. That's a peculiar discrepancy between the way they describe the world. Alice describes the world as only this half space here. She describes Bob as asymptotically approaching the horizon. And Bob says, nonsense, I simply fell through the horizon. I didn't get stuck here. Alice says he got stuck there. So there's a discrepancy in the way they think about the world. This doesn't seem much of a big deal. This is just a funniness about the way we draw coordinates. Let's go a little further. Let's introduce a bunch of Bobs. Here's a bunch of Bobs falling in with Bob. A whole bunch of Bobs. How does Alice see those Bobs? She sees the Bobs pile up at the horizon. She sees a grand pile up at the horizon where they all seem to slow down and get stuck at the horizon. The Bobs, they never heard of such a thing. They just said, we sailed nicely through the horizon, felt nothing at the horizon. This is what the equivalence principle says. The equivalence principle says that if there is a gravitational field, it must somehow do the same thing. If there's a this is not a gravitational field, but if there is a gravitational field, it must somehow do the same thing. All right, so let's move on now to non-uniform gravitational fields. The Earth's gravitational field is not uniform. If we only look at the world over a small area, we can approximate it by a uniform gravitational field, where the gravitational field points in the same direction, has the same value everywhere. But if we want to think about the Earth, we have to imagine that this acceleration is radially symmetric, that we're sort of being accelerated outward away from the Earth in a radial way. You can't really draw that. It doesn't really quite make sense. But what we can do is we can take the Earth, draw it as a sphere. The sphere is the floor, if you like. And imagine at every point, if we draw a small little patch near that point, we should be able to use this picture. What this picture says is that Alice out here looking at this, what will she see? She will not be able to see, when I am not now talking about the Earth, of course I am talking about a black hole. I shouldn't have called this the Earth. I'm now talking about a black hole. I hope the Earth isn't a black hole. All right, so we're talking about a black hole. The horizon over here simply becomes a surface over here. And what does Alice see? Alice sees Bob, and Bob slowly, asymptotically approaches the horizon. Gradually, he gets closer and closer. Incidentally, as he gets closer and closer, I might add that what happens to him is he gets contracted, flattened, pancaked, and eventually just gets, roughly speaking, plastered against the horizon. Plastered against the horizon. It takes forever in her frame of reference, in her watching of this. It takes forever for Bob to reach the horizon. And if there are a lot of Bobs, they all pile up. In fact, it's worse than that, or perhaps maybe not worse than that, maybe it's better than that. Everything that ever fell toward the black hole, everything that made up the black hole, everything that fell inward, that composed the mass of the black hole, Alice sees as piled up at the horizon. What does Bob see if Bob jumps in? Well, Bob sees exactly the same thing that he would see here. The equivalence principle says that Bob sees nothing special at this point here. He sees no pileup. He sees no dramatic event happening. This is a little bit odd. Physicists have known this for a long time, and they have simply said the words they use is, this is an artifact of funny coordinates. Is it an artifact of funny coordinates, or does it represent two different descriptions which have to be made compatible? I would submit that the answer is the latter. We have to have a description of the world in which both of these descriptions simultaneously make sense. So we're going to talk about that. All right, a little more now. Let's go a little further. From Alice's point of view, all of this pileup here that piles up at the horizon is hidden information. It's very hard to see, incidentally. The reason it's hard to see is because it all gets redshifted. Redshifted means the radiation from it becomes longer and longer wavelength, and it just gets very hard to see. So when I say Alice sees it, I mean Alice's mathematical description of the world or of the black hole involves this sort of picture, but you really can't see it. It's too dim, things are too close to the horizon, radiation just takes too long to get out, and so this becomes hidden information. What's stored near the horizon there in this very thin layer just above it, is all of the information, and that means all of the distinctions that might have to do with the different things that could have fallen into the black hole. They're all stored there, and they're stored there essentially forever. Well, not quite, as we'll see, but they're stored there and they're hidden information. That must mean that the black hole has entropy. Entropy and hidden information are the same thing. So, we come to an interesting conclusion. The black hole hides information, must give rise to entropy. Entropy is a quantitative concept. It's the logarithm of the number of bits of information that can be hidden in this way. For our purposes, a bit of information could just be an elementary particle. How much information can be stored at the horizon of a black hole? At first sight, you might think that because you can get closer and closer and closer, this is a kind of sedimentary glup, sedimentary sediment that settles closer and closer to the black hole, you might think you can store as much as you like. But it's not true. There's a limit to how much information can be stored at the horizon of a black hole. It was discovered by Bekenstein around 1972, elaborated by Stephen Hawking, and it's probably one of the most important contributions to physics of the 20th century. I'm going to take you through the derivation. We're going to do it. We're going to do the derivation, the mathematical derivation, with all the fancy calculus and group theory and integral equations and category theory. We're going to use category theory. All right, so we're going to go through the calculation of how much entropy can be stored at a black hole. If I'm successful at this, if I can get this across, even if I can get it on the blackboard, I will be very happy. First statement, which I didn't write down and I was supposed to write down before, is there's a connection between the radius of the black hole, and that means the radius of the horizon, the radius of the place where the pileup takes place, and the mass of the black hole. Here's the formula. The radius of the horizon is equal to twice the mass of the black hole, Newton's constant, divided by the speed of light squared. Okay? In what follows, I am going to ignore all numbers like 2 and pi. That's okay, because I'm only interested in the moment for orders of magnitude. So let's ignore irrelevant, for my purposes, irrelevant things like 2, and just say the radius of a black hole is proportional to its mass. We could use another symbol. We could use not equals, but sort of equals. Sort of equals means approximately equals. All right, now what we're going to do, we're going to start with a small black hole. And then we're going to build up a bigger black hole, and we're going to build up a bigger and bigger black hole by dropping stuff into it, one bit at a time. And each bit is going to be required to be only one bit of information. The bits that we throw in should only convey one bit of information. For example, we could throw in photons. You can have polarization. A photon can have a polarization. It can be a photon moving that way can be polarized this way or that way. We could take the bit of information to be what the polarization of the photon which fell in was. Okay, so we're going to throw in photons, and each photon brings in one bit of information. This photon here, this wave here, is supposed to be the wave-like character of the photon. But if we're not careful, if we throw in photons of short wavelength, they will actually have more than one bit of information. For example, if we throw in, just imagine we throw in a photon, imagine a photon is an ordinary particle. If we throw in a photon, then there's not only the information about whether the particle was there, there's also the information about where it fell in. Where it fell in might have, there may be many digits to how many digits we want to keep track of in the angular position of where the photon fell in. That's a lot of information. I had not intended to throw in that information. The way to avoid that is to use the Heisenberg uncertainty principle and to say, let's take a photon whose wavelength is such that it's comparable to the radius of the horizon. A photon like that is delocalized, doesn't have a definite position. It has a fairly definite momentum, a fairly definite other thing, but it doesn't have a well-defined position. In fact, its position is spread out over its wavelength. Therefore, when that photon falls into the black hole, it conveys no information about where on the horizon it fell in. So we're going to take photons of wavelength lambda. Lambda is the wavelength, and that wavelength is going to be chosen to be the radius of the black hole. Now you can say, why don't you use even bigger, longer wavelength photons? The answer happens to be that wavelengths longer than lambda will just bounce off the black hole and won't go in. That's something you can calculate, has been calculated. And so if you throw in photons of wavelength r, there'll be no information about where they fell in, but they will go in. So that's our game. And now we're going to ask, when we throw in a photon of that wavelength, how much does the radius of the black hole change? We're going to do that calculation. All right, so what we have to know is the following. We have to know the energy of a photon of wavelength lambda. This is the most, this formula here is also an ancient and venerable formula. I think it's due to Einstein. And it's the energy of this photon is Planck's constant times the speed of light divided by the wavelength. Now, if you don't know that formula, I can't do anything for you. If you do know that formula, then we can proceed. In fact, even if you don't know that formula, now you do. So the formula is not finished. We should divide by lambda. The smaller the wavelength, the bigger the energy, and the wavelength is r. So the photon that we threw in has energy h bar c over r. That means that the energy of the black hole has changed. We've thrown in, so let's write the change, delta, little delta stands for change. The change in the energy, now it's the energy of the black hole. That's just the energy we threw in. So it's also h bar c over r. I was sure that Paul would tell me that I forgot a 2 pi in this formula, but I did. Okay, delta E equals h bar c over r. Now, how much of a change in the mass does that correspond to? Well, for that, we use a formula that you do know. E equals mc cubed. No, mc squared, sorry. E equals mc squared. So that means that the change in the mass is the change in the energy divided by c squared. So we can now write, let's put a comma here, delta, the change in the mass of the black hole, is h bar c over r divided by c squared. That's h bar over r times c. That's the change in the mass of the black hole. What's the change in the radius of the black hole? Well, here we know the connection between the radius and the mass. If the mass changes by a certain amount, then the radius changes by the same amount times g over c squared. So now I can write about how much the radius changes. Delta r is equal to h bar over r times g over c cubed. Now it is c cubed. Now it is c cubed. One c comes from here, and two c's come from here. And that's the form. Do I have it right? I think I have it right. Yeah. Yeah, okay. This is the change in the radius. So what I found out is that when I drop one of these photons in, its radius changes by this much. But now I'm going to do a trick. I'm going to multiply by r. So let's multiply both sides by r, and we're going to get something that's you may not find particularly interesting. But if you think about it for a moment, you realize that what's on the left-hand side here is not just r times the change in r, it's the change in the area. The change in the area. The area is proportional to r squared, and the change in the area is r times the change in r. It's a little calculus formula. So what do we have here? We have the change in the area of the black hole. Let's erase what's in between. And on the right-hand side, r has disappeared. We just have a universal constant, a constant which is made up out of Planck's constant, the Newton constant. Did I tell you that G was the Newton constant? If I didn't, you should have asked me. Please ask me. If I do that again and I forget to tell you what something is, just blurt out, what the hell is that? Okay, the change in the area of a black hole, when you change the amount of information by 1 bit, is this universal constant here, h bar g over c cubed. What are the units of this quantity? The units are, of course, area. This must be some area. It is an area. It's a number which is about 10 to the minus 70 square meters. That's also called the square of the Planck length. It's called the Planck area. So every time you increase the amount of hidden information, we might as well now call it the entropy. Every time you increase the hidden information by 1 bit, you increase the area of the black hole by this amount. Well, after you do this many times and you build up from, let's say we start with a tiny black hole and we build up a big black hole, the answer is that the area must be the number of bits that we threw in times this Planck area. We can write it a different way. I'm going to erase some things over here. I'm not ready for the next blackboard yet. I'm going to erase over here, and what I'm going to write is that the area of the black hole is equal to the number of bits of information we threw in. That's called the entropy. It's called the hidden information. The entropy, the symbol for entropy is S. I don't know why. I don't know where it came from. Somebody told me that it came from, that it represents Sadi, S-A-D-I, Sadi Carnot. I think it's Sadi. Is that the way you say it? Sadi Carnot, who was the first to introduce entropy into physics. And I asked, well, why did they call it C? Well, it turns out I think the person who named it was named Clausius and didn't want to name it for himself. So I think this is true. So it's called S. S is entropy. It's the area divided by the area of 1 bit of information. There's a total area. How many bits of information can you stick on it? And that means divided by h bar g and a c cubed, which I'll take from the denominator and stick it up in the numerator because that's where it goes. Now, this formula is not exactly right. It's not right because I didn't keep track of the constants. And in fact, I didn't have enough control of the physics and the mathematics to keep track of the constants. But Stephen Hawking did keep track of the constants and discovered that there was a 4 in the denominator here. This is extremely interesting. I mean, it's more than interesting. It is, as I said, one of the great discoveries of the 20th century physics, that a black hole has an entropy which is proportional to the area of the black hole, the area of the horizon of the black hole. Now, that's unusual. The reason it's unusual is most systems, for example, the room here, the room is full of molecules. The molecules are too small to see, and so there's a lot of hidden information. How much information? Basically the number of molecules. How many molecules? Well, it's proportional to the volume of the room. In most cases, in fact, all cases that I know, besides this, as a rule, the entropy of a system is proportional to its volume. This is something different. This is something we never saw before, that the entropy of a system is proportional to its area. Now, it does occur elsewhere, but it's unusual. All right. Any questions? Yes? I am a teacher. This is what I do.
When you went from the delta A up there,
yeah.
it's as if the constant's the wrong way up.
Did I get them in the wrong place? It should be the area divided by this, right? Yes?
Yeah.
Okay, so,
The area divided by.
hmm?
S is the area divided by.
Oh my Lord. Thank you. S is the area divided by the Planck area. The entropy is the area divided by the Planck area. In other words, the black hole horizon is, its area is equal to the number of bits of hidden information times the Planck area. Whoops. Okay, let's go a little bit further with this. Black hole has entropy, it has energy. It has energy because E equals mc squared, and the black hole has a mass. It has energy and entropy. Thermodynamics tells you that when anything has entropy and energy, it has temperature. And one can calculate the temperature. I'm not going to do the calculation here. I could show you how it works. It comes from a basic relationship between energy, entropy, and temperature. For those who know, it's dE equals TdS, but never mind. You can calculate from these things, you can calculate the temperature, and the temperature of the black hole is h bar c cubed, I believe, over some number times the mass of the black hole times g. That is the temperature of the black hole. Now, the reason we're interested in the fact that the black hole has temperature is I'm not so much interested in the exact formula. That's not the issue here. Just the mere fact that it has temperature means that it shines like a warm body. It shines like a black body. It shines like a heated object. Shines means it gives off radiation. It has a luminosity. All right? Given that it has a luminosity, it means that it gives off energy. Any warm body, if put in empty space, will radiate its energy away. So this black hole, with a temperature, will start radiating its energy away. That means the black hole evaporates. We could calculate, if we wanted, how long it takes for the black hole to evaporate. It's a very, very long time. But this was the discovery of Stephen Hawking sometime around 1974. And as I said, it was really quite a monumental discovery. Black holes have entropy, they have energy, they have temperature. They behave like a bucket full of warm water or something like that. Now, if there are no questions, I will go on. Let's come over to this blackboard here. This is bad news for Bob. Well, maybe it is, maybe it isn't bad news for Bob, but let me tell you why it might be bad news for Bob. Bob, remember, is the fellow who jumps into the black hole. He's the one who likes to jump across the horizon. Okay, why is it bad news? Well, let's think about this for a moment. Here's the black hole, and if you go far away, you will discover photons coming out of it. This is the radiation. This is the black body radiation that comes out. And the black body radiation has a certain temperature. We wrote down what the temperature is. It's h bar c, whatever it is, h bar c cubed over mg. Associated with that is an energy for each photon. The photons have about that wavelength, and they just fly out. But a photon that appears over here with this temperature, it's also the energy of the photon. Temperature and energy roughly related. This is also the energy of the photon. When a photon materializes at the horizon and goes out, it loses energy. Why does it lose energy? For the same reason that if I threw this chalk up in the air, as it rises, it loses kinetic energy. The gravitational field is pulling it back, and the result is that it loses kinetic energy. The same thing happens to the photon as it goes out. It loses kinetic energy. But by the time it gets out, it has this much kinetic energy. That must mean when it started near the horizon, it had a lot more kinetic energy. And if it had more kinetic energy, it effectively means that things were much hotter near the horizon. Bob falling in will not encounter a photon of this energy. This is very low because of the mass in the denominator here. He will encounter a photon of much shorter wavelength, much higher energy, Just because if it got to be of this energy by the time it got out, it must have been much higher energy when it left the horizon. And in fact, you can calculate the energy of a photon, or let's just call it the effective temperature. The effective temperature at a distance d from the horizon, little d, that temperature is h bar c, that's not the important thing, divided by d. The implication is that as you go closer and closer to the horizon, the temperature gets hotter and hotter and hotter. That could be bad news for Bob. Bob, who's going to jump in, will apparently encounter a huge temperature as he gets near the horizon. On the other hand, something very peculiar, because the equivalence principle tells us that when Bob falls through the horizon, discovers nothing special, just empty space near the horizon. And so we have a kind of conflict. We have a real conflict, I think. Well, I don't think it's a real conflict. I think there's an answer to it. Let's just go back for a minute. What is Alice's description of this black hole? A pileup happens. The pileup carries lots of entropy. Apparently, it carries a lot of temperature. It's very hot near the horizon. Where did this all come from? It came from the assumption that information is conserved. How did we use information was conserved? Well, we said anything that falls into the black hole gets piled up near the horizon. It doesn't get lost. So information conservation, on the one hand, tells us, or tells Alice, that there's a pileup near the horizon. Bob, on the other hand, uses the equivalence principle. And he says, Einstein tells me that a gravitational field is nothing but a field of acceleration, and under those circumstances, I should discover nothing special when I pass the horizon. Now, I left out one concept here. I didn't intend to leave it out. I just went too fast. The center of the black hole. What's happening at the center of the black hole? In the approximation where the gravitational field is uniform, the center is infinitely far down. Right? In the approximation where the gravitational field is completely uniform, the center is infinitely far away. But if we take into account the curvature of the Earth, or the curvature in this case of the horizon, the center is somewheres finitely down. So somewheres in the center, things are finite, and according to the standard rules of general relativity, Bob should discover when he falls through a singularity at the center. The singularity is a very nasty point. Let's not worry about the mathematics of it. Let's just say that gravitation, as you get close enough to that point, becomes so strong that it tears you apart, pulls you apart like a toothpaste. Singularity is a bad place. Where is the singularity on this diagram? Where is the singularity here? I'm going to show you where the singularity is, and I'll show you why Bob is in big trouble, not because of those high temperatures, but because of the singularity. The singularity is over here. That's the singularity of a black hole in this diagram. Think about for a moment what happens if Bob finds himself back here. If Bob finds himself back here, that means inside the black hole. If he finds himself inside the black hole, he cannot escape. He cannot escape the singularity. To escape out here, he would have to go faster than the speed of light. He can't do that. He's inevitably going to crash into this. No matter how he moves, he can't get away from the singularity. So that was one more point that I meant to stress, that there's something going on at the center of the black hole, which is very deadly for Bob. But according to this story here, temperature, it's at the horizon of the black hole where Bob runs into trouble. Well, which is it? Bob is not going to survive falling into the black hole. That's for sure. But is he going to get himself in bad trouble at the horizon because of this? Or is he going to sail through the horizon freely and find himself destroyed at the singularity? That's the puzzle. That's the conflict of principle. That's the puzzle that that this lecture is about. Okay, which description is real? We could take a poll. Let's take a poll. Everybody has to vote. Everybody has to vote. Which is the truth? Is the truth that Bob runs into trouble and gets killed at the horizon? Or is that just a crazy artifact of silly coordinates? Or does he get killed when he gets to the singularity? So I will ask you to raise your hand. For those who think that he gets killed at the horizon, raise your hand. How about those who think he gets killed at the singularity? I thought so. There's a very strong tendency, for one reason or another, to believe that the description, that Bob's description is better than Alice. I don't think it's sexism. For some reason, people tend to prefer the Bob description, the description falling in. Why it is, I don't know. In my opinion, both of them have to be made consistent. They have to be consistent. And so let's talk for a moment about the possibility of making them consistent. And I will show you that they are consistent. Okay, so here's our horizon. And using the formula, which I erased, that the temperature is equal to, what did I say it was? H bar C cubed over D, over the distance from the horizon. That's the distance from the horizon. Let me take the place here where the temperature is larger than a certain temperature. What temperature? Oh, the temperature at which Bob will be scalded. The temperature at which Bob, let's do something a little bit simpler. Instead of Bob, let's just drop an atom in. According to this picture, if the atom gets close enough to the horizon, it runs into a place where the temperature is hot enough to ionize it. So an atom falling in, according to this picture, will get ionized at a certain distance from the horizon. That distance is the temperature where the black hole, or where this formula becomes what? 13.5 electron volts, or whatever it happens to be, the ionization energy. Okay. On the other hand, the other picture says that the atom just sails through. Let's do an experiment. Let's do an experiment of the following kind. Charlie, let's see, Alice is here, and she's watching all of this. Charlie is going to illuminate the atom with radiation that will bounce off so that Alice can see what's going on. This is how you see things. This is how you find things out. You illuminate the system with, let's say, photons or with radiation, and take a look and see what's going on. Question, will Charlie's radiation come back to Alice and say the atom was ionized, or will it say that the ion was unionized? Okay, so let's see if we can analyze it. In order for these photons to see what's going on in this small distance d here, the photons have to have a small enough wavelength that they can resolve this distance. You can't see something of a given size with photons of longer wavelength. So the photons have to have a wavelength d, or smaller. Lambda of Charlie's photons has to be d or smaller. From that, we can compute what the energy of the photons is. The energy of these photons will be, perhaps no surprise, the energy of those photons will be h bar c cubed over d. Did I get that right? h bar c over d. The energy of the photons is h bar c. Is this right? This can't be right. C. It's c. It's c. Same thing. Same. All right, so here then is the energy of the photons that Charlie has to shine on this system. What's the problem? The problem is that these photons that Charlie uses to illuminate the atom are of a high enough energy to ionize the atom. In the attempt to try to find out whether the atom was ionized, quantum mechanics, this is the complementarity, this is the uncertainty principle. This goes back to what I originally started with, the experiment to try to see that, that the particle fell through without being ionized will itself ionize the atom. This is a very, very general pattern. any attempt to try to discover whether there is a pileup over here by shining light or anything else on the system to see what's going on will produce exactly the effect that the experiment was designed to show didn't happen. For example, when Bob falls through, Alice may want to find out whether he gets killed or roasted or fried or whatever it is at the horizon here. The only way she can find out is for Charlie to illuminate Bob with radiation and send it out to him. The answer will be that the radiation that Charlie has to use to see whether Bob was fried will have an energy hot enough to fry Bob. So I'm going to stop around here and tell you that as far as we can tell, all evidence is that both descriptions are consistent, but they're complementary. Complementary in the same sense that the wave-particle theory of light is complementary, complementary in the same sense that you can describe an electron by a position or a velocity, not both. What we're learning is you should not try to think of a description of this black hole simultaneously from the point of view of Alice and Bob. If you try that, you will run into trouble. One or the other. Either you do or you do not try to find out if Bob was roasted. If you don't try to find out, Bob will fall through with no trouble, but Alice will never know. If Alice does try to find out, she will roast Bob. The evidence is that these two descriptions are not incompatible, but complementary. I will stop at that point, I think. I have lots more, but we're going to stop there. Could I? Oh, I can. You want to go on for another 5 or 10 minutes? We started at 7:30.
Everybody has to vote.
Yeah, okay.
Yes?
This is putting it.
Should he go on or not?
Yes.
All right. Okay, we can go on for that long. Oh, okay. That's right.
Okay, what about no?
All right. Well, okay, that's very nice. All right. What I promised to talk about in the title of the lecture was the holographic principle. We've not talked about the holographic principle. The holographic principle is another extremely odd, but apparently really, what shall I say, a consequence, a logical consequence of what I've told you. So let me tell you what the holographic principle is. It again has to do with where information is really stored and how much information can be stored, but not for the moment in the vicinity of a black hole, but just in empty space. Let's suppose we have a region of space. There's a region of space. I chose it to be spherical for simplicity. It could be a very big region of space. It doesn't have to be small. It could be big enough to contain galaxies and planets and all that kind of stuff, but of some finite radius sphere. And the question is, what's the maximum amount of entropy that can be in there? The maximum amount of entropy that can be in a region is the maximum amount of information that can be hidden. It's also a measure of how many degrees of freedom it takes to describe that region of space. The maximum entropy of a system is, roughly speaking, how many distinct coordinates does it take to describe that system. All right, so there's our question. What's the maximum entropy can be here? It could be in the form of gas. It could be in the form of Swiss cheese. It could be in the form of people, whatever. How much hidden information can be, or how much information, period, can be inside, or how much entropy can be inside there. So here's the thought experiment we're going to do. First of all, let's suppose that the entropy initially was S in. In stands for initial. The initial entropy is called S in. Now let's imagine that we have a large shell of material. We create a large shell of material out of whatever material we have available, interstellar gas, whatever it happens to be, and we arrange it in a shell, and then we project it inward so that it starts to fall in toward this region. Now let's choose the mass of the shell to be exactly right so that when it's combined with the mass in here, it's exactly enough mass to make a black hole of precisely the same radius. You have to trust me, that's possible. There's no ambiguity about it, and there's no controversy about it. It is possible to create such a shell which is just right to create a black hole of exactly that size. So the shell comes in, crosses the radius r, and leaves a black hole. What's the entropy of that black hole? The entropy of that black hole is the area of the region, just the same formula, times c cubed over h bar g. Most important is that it's the area in Planck units, 4 times that. It's the area in the units of this very, very small Planckian area. What does it say? First of all, the second law of thermodynamics says that the entropy after you do this must be bigger than the entropy before. Entropy increases. Therefore, we learn the following, that the initial entropy must have been less than or equal to, could not have been bigger than the area times this other stuff here. That's a limit. That's a limit on how much entropy could have been in that region of space to begin with. It didn't really depend on whether there was a black hole there or whether there was a shell of matter there. Even if the shell of matter wasn't there, just the fact that we could have created it and sent it in tells us that the entropy in a certain region of space cannot be bigger, can never be bigger than the area of that region in Planck units. That's really interesting because in all other physics, the maximum entropy of a region of space is proportional to the volume. It's also true in most other physics that the number of degrees of freedom that it takes to describe a region of space is proportional to its volume. We have found out by the series of indirect arguments that any region of space can be described by a collection of degrees of freedom which are no more numerous than the area of the region in Planck units. That led to a conjecture. It led to a conjecture that any region of space can be described by some kind of theory describing degrees of freedom on the boundary of the region of space. That is what was called the holographic principle. Holographic because it's like a hologram. That was a conjecture. It was a, you might even call it a speculation, which is worse than a conjecture. But it was in 1994 or so that this conjecture was put forward. Most people at the time thought it was a screwball notion. But it took a couple of years, basically until 1998, until a young Argentinian physicist whose name you should know. I ask people, do you know who Juan Maldacena is? I'm talking about physicists or physics groupies and so forth, and often they don't. Juan Maldacena is perhaps the greatest physicist of his generation. I won't tell you how old he is. He's younger than me, so he's not necessarily greater than me, but he is certainly the greatest physicist, greatest theoretical physicist of his generation. I'm going to write his name. Maldacena. Mal stands for bad or something, but I don't know what is this? What does bad of, what is Sena? It's Italian, I think. Bad of Sena? Anyway, his first name is Juan. Juan Maldacena produced a perfectly rigorous description of this for a particular particular kind of space-time called anti-de Sitter space, but that's not what's important. What's important is he dotted the I's, crossed the T's, and found an extremely precise mathematical description of the degrees of freedom on the boundary which would describe a region of space. And indeed, it turned out that there were no more of them than 1 per Planck area on the region of space. So in some sense, the world is really described by a kind of holographic description on its own surface. Just to make it graphic, everything in this room, there is enough degrees of freedom on the walls of the room to describe everything in the room. It is as if the walls of the room could be thought of as a hologram describing what's happening in the interior. Okay, so we got through the holographic principle. Thank you.
So while you're thinking about questions to ask the lecturer, I have 3 comments. The first is Juan Maldacena will be giving the beta lectures this fall.
I wish I would be here.
We'll see if Lenny is right.
You won't find out I'm right. I'm telling you.
The second comment is tomorrow's lecture will begin at 4:30 in this room, but there's a class that ends at 4:10, and the audio-video people are going to be moving quickly to get everything ready. We won't be opening the doors until 4:15, and so we ask that people not interrupt the end of the class. The third is that there will be a reception in the atrium between Clark and the new Physical Sciences building. There will be a bunch of people here. There won't be enough food for all of you, but Lenny has promised he'll stay until long after midnight to answer any further questions. Right now, after
now?
Oh, I had 3 comments. The second comment referred to the lecture tomorrow. The third comment referred to after the lecture today.
Yes.
Do we have questions for Lenny? Yes.
Okay, so you said that if something is falling, past the horizon, it can't cross back out. But simultaneously, you've said that these black holes are radiating temperature. So if things have fallen in, you're adding energy to the system.
In one description, things fall in. In the other description, they never get in. In Alice's description, which is appropriate to somebody who stays outside, remember, somebody who falls in doesn't see this radiation. Somebody who falls in has a short amount of time before they're squashed to annihilation at the singularity. Somebody who stays outside sees the radiation. So we can ask, what is Alice's description of things? Alice says there's a pileup, and all these degrees of freedom pile up at the horizon. They stick around there, and gradually, sort of one by one, they boil off. Bob, who fell into the black hole, says, I got killed. Well, he doesn't say this, but he says I was destroyed at the horizon, at the singularity, and simply wasn't around long enough to know whether the black hole evaporated. He's gone in a small fraction. The amount of time for a solar mass black hole that, the numbers here are a little bit deceptive. A solar mass black hole is about 1 kilometer. You might think that a meter's worth of human being could fall through a horizon 1 kilometer big. No, it turns out that the tidal forces at the horizon would be so strong that they would tear you apart. But that's not the important thing. A much smaller thing could fall through. A bacterium could fall in. How long would the bacterium have before it fell and hit the singularity? And the answer is approximately the light transit time across the black hole. That would be about a millisecond, I think. I think it would be about a millisecond. For 1 kilometer, anybody can do that fast in their head? 1 kilometer, I think it's about a millisecond. So that bacterium has about a millisecond. How long does it take the black hole to evaporate? Oh, just 10 to the 75 years or something like that. So the answer is that Bob has no experience of the evaporation. It's Alice whose story involves the evaporation of the black hole. And her story is that there's a pileup at the black hole, and the pileup gradually evaporates off the surface of the black hole. So it's quite confusing, but it's quantum mechanics. Quantum mechanics is supposed to be confusing.
Yes.
So how do we know that the black hole has a uniform radius?
Has a what? A uniform radius. Okay. How do we know that a black hole is a sphere? Is that the question? Yeah. Of course, if it's a rotating black hole, which most black holes are, then it's a sort of oblate. Oblate? Do I have it right? Oblate is the broad one, and prolate is the skinny one. Yeah. It's an oblate spheroid, which means a sort of ellipsoid. But if it's not rotating, it is spherical. Now, one answer to it is a black hole is a thermodynamic system. A black hole is a thermodynamic system, and that means it's a system which will come to thermal equilibrium. When a system comes to thermal equilibrium, it becomes featureless. If a system is spherically, forget whether it's spherically symmetric. If an idealized system, such as a water droplet in space or something like that, which is a thermodynamic system, is allowed to relax to thermal equilibrium, it will be perfectly round. One of the reasons is that the temperature has to be uniform everywhere across it. Temperature, pressure, and so forth, and so it will achieve a perfectly round behavior. And the black hole is also a thermodynamic system which comes to equilibrium. The words that John Wheeler used was a black hole has no hair, which means it's sort of bald like my head and perfectly round.
And how do you describe the region between the singularity and the horizon?
Yeah, okay, but that's this region here. And as long as you don't get, how does who describe it? Alice or Bob? Charlie, how does who describe it? Has to be Bob. Alice said Alice has no use for it. She never heard of it. She said the world ended over here. Bob, yes, and what does Bob say? Bob says it's just flat space. It's just normal vacuum, normal empty space, except that it starts to get curved and distorted and deformed to the degree where it will become very harmful as he gets close to the singularity. But as long as it's not too close to the singularity, it's just ordinary empty space.
So in some sense, the gravitation force is... In some sense, the gravitation force is increasing?
Can you... I'm a little deaf.
He asked, in some sense, is the gravitational force increasing?
Yes, in some sense, the gravitational force is increasing, but it's increasing... in particular, the tidal force is increasing. The tidal force is the thing that pulls you apart. The tidal force is increasing. But if we don't think about the tidal forces, if Bob is small enough that the tidal forces don't disrupt him, then he's just in free fall. In free fall, there is no gravitational field. If you jump from the ceiling and fall down to the floor, you don't realize, with your eyes closed, of course, you don't realize that you're falling until you hit the floor. So Bob is in free fall. He says everything is perfectly okay until he gets too close to where the geometry becomes highly deformed.
And one can show inevitably in finite proper time he's sailing along and then So one more question. We should deconvene. Yes, Carl.
It's been a beautiful talk. Thank you very much. But what experiment can you do? How can you use to prove that you're wrong?
There's none.
But the matter is falling into black holes. We know there's accretion in black holes.
Yeah.
What can we look for?
No, I don't think this is going to say anything new. But what I would say is this has implications for cosmology. Remember, in cosmology, I talked last time a little bit about cosmological horizons. Okay? Everybody is falling through somebody's horizon in cosmology, in de Sitter space. Am I talking a language you are familiar with? No. Okay. All right. In cosmology, everybody is falling through somebody else's horizon. And so just the fact that we don't get destroyed every fraction of a second means that horizons are smooth. You know, you're asking a question which I don't know the answer to. How do you make empirical science out of any of these questions? This issue has been around since 1974. It has invaded physics to the point where I would say the majority of papers in theoretical physics, including condensed matter physics these days, is using the mathematics of horizons and so forth. But it really is troubling. All right, let me just put it bluntly. It's very, very troubling that we've entered such a range of parameters that it seems absolutely out of the question to do experiments. Even if I told you that you could do the experiment of jumping in the black hole, I think you would tell me, well, get me the black hole and you try it. But you know, it's a problem. I don't know the answer.
Silly question. If space-time is granular, and then you try to use the holographic principle, doesn't it sound as if the surface area is smaller, has to be smaller than the grain to get all that information?
The whole surface area is smaller than the grain?
No. I mean, if you look at the inside of the space, and say, okay, how many grains do we have? And then we put
in the inside of the space. Yeah. There are many, many more grains, apparently, than on the surface of the grains. That's right. And what this is telling you is that those grains cannot be independently excited. There just aren't enough the degrees of freedom so that every independent place can be independently excited. Yes, but there's another way to think about it, which makes it less odd. If you try to excite independently degrees of freedom in every region of space, you'd make a huge energy. You'd make an energy which would be bigger, which would make a black hole bigger than the region that you're talking about. Right. So it's consistent and right.
Okay, so there will be food for some of you. Leonard will provide food for thought for the rest of you.